Our last presentation from this session is from George Athanasopoulos from Monash University, and he's been looking at forecasting prisoner numbers using a grouped time series approach. So thank you, George.
Thanks, Hamish. Hope you can hear me, yep. So I have drawn the sort of short stick of the draw, and I'm the only thing staying between this and your lunch, so I'll try and finish on time. And I also got to sort of make a little bit of a declaration that my presentation is a little bit on the technical side, and I'm glad that technicality has been increased from this morning's session as we're going along. So we are on the right path. The technicality of the presentation will just get a little bit even hairier. But hopefully what I'll aim to do is to give you a broad picture of the methodology that we put forward and use to forecast prison numbers in Australia, and give you a general feel, talk you through the technicalities and give you a general feel of how broad this methodology and how general it is and how applicable it is. So this is joint work with Tom Steele, who's a master's student at Monash University, was a master's student at Monash University, is now at Ernst & Young, and Don Weatherburn from Boxer, and obviously all the errors in the paper are Don's fault, right? So what do we aim to do in this paper? So we aim to produce a set of accurate forecasts, but we also want our forecasts to be detailed. What do I mean by detailed? We want to produce forecasts for attributes of prisoners that are of interest to the policymaker. And I'll talk about those attributes as we're going along. What I hope to do by the end of the presentation is to actually convince you that the level of detail and the coherent nature of our forecast, and I'll talk to you about what I mean by coherent nature, enables informed and importantly aligned decision making across multiple departments and levels of management, whether that is a strategic, tactical, operational level. Okay. So here's a time series of number of prisoners in Australia. This is at the aggregate level across time. I look at this time series, I can very easily take a time series model to it, or a regression model, a structure model, or whatever you like, and sort of project that trend forward, and I can get a fairly accurate set of forecasts. I don't think I have any problem doing that. However, below this time series lies a rich list of information that I, as a policymaker, I'm interested in. As a modeler, I want to take advantage of, okay? So if I looked at prisoners by state in this graph here, I can see various dynamics revealing themselves. So, flattening of time series, or, higher trends, higher growth rates, and so on. This is by legal status, so you can see there's a difference in the dynamics between the two, and the policymaker, you would be interested, whether a prisoner is in the system and is still in remand or has been sentenced. Then we have building wards or wings of prisons for males and females and so on, or having Indigenous status of our prisoners. Now, further to that, even more information comes to light when we interact these attributes. So in the first row here, I have, let me go back. In the first row here, we have interacting two attributes, so it's state by legal status, and you can see now that I'm getting more time series and I'm getting more information that I want to work with. Here we have three-way interactions, and here we have bottom level data, which is the most disaggregate I can go. I've interacted these four attributes, so I've disaggregated all the way down, and each line of these is a four-way interaction. I've only picked some of these. It's not all the time series that you see. And the other thing that I want to point out is that when you see things like this, it's just a matter of scale. If I take that and I expand it, then I'm going to see various time series dynamics and properties that will reveal themselves. Okay, so by looking at demographics and looking at our prisoners, we have a total of 243 series, starting from the aggregate to the state, sex, legal status, Indigenous status, down to the very bottom level of 64 time series. Another way we can disaggregate our prisoner data is by looking at the ANZ Standard Offence Classification Code, where we take our very aggregate, and that disaggregates into divisions, and then further into subdivisions, and further down to groups. So you can see the difference in these two aggregation structures. They're different in nature. The factors here are what we call nested factors. So we go from one which subdivides, which subdivides, which subdivides. In this one up here, we have factors that cross. We have interactions between these four factors. So what we do, we distinguish between these two, and we call this a hierarchical time series, where it's got a hierarchical structure to it. It's always increasing in size. This one we call a group time series, okay? And it's an important distinction between the two. Okay, so we're not alone in the world with this type of structures. We see them across many, many industries. Data sets that I've worked with is tourism data, where we have tourist flows by state crossed by the purpose of travel, and that gives us a total of 555 series that we need to model. Another project is forecasting student numbers at Monash University, where we have, Monash the university is interested in forecasting students at faculty level, campus, funding source, and so on. And we have a total of 152,000 time series that we need to model and forecast altogether. The important bit to understand is that these are not independent series. These series come from an aggregation structure. They're related by aggregation constraints, okay? And that's what we want to take. We want to preserve in some way, and we also want to take advantage of it. Okay, so challenges. We have a large number of time series to forecast. We want some flexible forecasting process using all the information available to us. I don't just want to go to the aggregate level. I just don't want to choose one level. I want to use everything I've got, right? I want to be efficient. And we want our forecast to be coherent. What do we mean by coherent? We know that our data by nature adds up. You know, number of prisoners across the states adds to the aggregate. If I generate forecasts, I want my forecast to also be coherent, okay? What's the key idea of the methodology that I'm going to implement, and the methodology that we propose in this literature is that, in contrast to traditional bottom-up or top-down approaches, where you choose a level, you generate forecasts, and then you aggregate those up or disaggregate down, what we're going to do is go and generate forecasts for all the time series I have, right? All the time series that live in my collection, I'm going to generate forecasts for, and then I'm going to take to those forecasts a process of reconciliation. I'm going to reconcile them so that they become coherent, so that they adhere to the aggregation structure that I started off with, okay? So the next 3 or 4 slides will be a little bit technical, but I'll try and step you through what the methodology does. So here's a very simple hierarchy. We have a total, which is subdivided into A, B, and C, 3 time series. The key concept here is that, that's a little bit of a fortunate use of colors, but I can construct all time series in my collection if I know the aggregation structure and the bottom level series. So those are the only 2 things I know to construct all the collection I have all the time series that I have in my collection. So let's formally define that. How do we do that in mathematics? So if your matrix algebra is a little bit sketchy, I'll walk you through this. So we have, these are our 4 time series from that hierarchy. So we have the total, and we stack them up in that vector. Now we're going to define this summing matrix, which reflects the structure of my aggregation, right? The aggregation structure I have, and we define this B as my bottom level series. So what this does is, this summing matrix pre-multiplies this B vector to give me everything that lives on my hierarchy. So this first row takes YA plus YB plus YC to give me Y total. This identity matrix takes these 3 and sticks them there, right? So for any hierarchical time series in that structure, we can write that all we need to know is the bottom level series, the aggregation structure in this summing matrix, and I get everything that lives in my collection, okay? Now, different to that is group time series, where we don't have that nice structure that I just showed you. But we have this type of thing. So here my bottom level series, AX, AY, BX, BY. This first row of my summing matrix takes those and adds them up to Y total. So I get that cell there, Y total. Now if I aggregate in this dimension, the horizontal dimension, I can go AX plus AY equals A, BX plus BY equals B. And that is reflected by this second row and this third row. If I go in the vertical dimension, because I have 2 attributes that I'm interested in, that is reflected by this row there, the third row and the 5th row. So I can write a summing matrix that actually captures group time series as well as hierarchical time series. And that is, again, I can write this very general equation up, and that is a great contribution in this literature because now we can handle both hierarchical time series, which we've done before, but we can also handle group time series, which is what we look at with prison data, okay? So that just summarizes what I've just said. Keep this equation in mind. I promise you there's only one more slide with characters on it, and then we'll move on to some results and some more general comments. Okay, so what we want to do, this talks about our data. We know that this is our bottom level data. This is how we sum the bottom level data, and we get everything that we have in our collection. What we want to do is take that into our forecasting world, right? We know our data will always add up. That's the assumption we start off with. So what we want to do is take that concept into forecasts. So here's a little bit more notation. Follow my words if you don't understand what a hat is. A hat is a forecast. So I generate what I do with my methodology, as I said. I take all the time series that I have and I generate forecasts for each one of them. And I label those as Y hat, right? These will almost certainly never add up. And why is that the case? We know our data is coherent. The only way to move that coherency forward is if I do something very, very simple. I do an naive forecast. I take all my last observations and I say these are my forecasts, right? That's a naive forecast. Then these by nature will add up. As soon as I start modeling each time series, whether it's independently, whether it's using regression models, whether it's multivariate, these forecasts will point in different directions and will not be coherent, okay? What we want to do is, what we aim to do is, if we can take those base forecasts, those initial forecasts that I have, and somehow map them down to the bottom level, right? Then I can use the S matrix and bring them back up, and then I have coherency, right? That's what I want to do. How do we do that? Well, we do it through this equation here. Let me step you through this equation. So we start off with a set of base forecasts. Y hat, remember, these are forecasts for every 243 series that I have, a forecast for every one of them. This, and I pre-multiply those by this P matrix, right? What does this P matrix look like? What does it do? Well, I'm telling you what it does, and I'll show you how it does it. It takes those forecasts for all 243 series, and it maps them only to bottom level. So it takes a dimension of 243 down to 60, I think it was the dimension that we had, right? How do we do that? Well, let me tell you how we do it. If we were doing a traditional approach, if we were using a bottom-up approach, I would use this P matrix. What does this P matrix do? It zeroes out everything else other than my bottom level forecasts. So what this matrix does is takes my bottom level forecasts and maps them to the bottom level. So it just retains those. Then I take the S and S times B will give me coherent forecasts. If I was using a top-down approach, I would use something like this. What does this do? This zeroes out everything else other than the very top forecast. That top forecast is redistributed to the bottom level by these P matrix, which has a set of proportions. So in my simple example of a three-dimensional bottom level hierarchy, so in this simple example, let me get back. Right, the proportion will take this Y hat and say I have three proportions, P1, P2, P3 is equal to 1, so the proportions, and I get forecast for that. Then I'm going to use this S matrix, and that will be a Y hat, right? So the thing that we want to notice here is that with both these traditional approaches, there's a lot of zeros in these. There's a lot of forecasts that from my initial base forecast that are getting zeroed out, right? And that is something that is a limitation to the traditional approaches. I choose a level I want to forecast at, and then I take those forecasts, I either aggregate them up or disaggregate them down, or if I'm doing a middle-out approach, I do some aggregating up or some disaggregating down. Can we do better than that? Of course, the answer is yes, and that's why I'm here to show you the method that we use instead of the traditional approaches. Now, this is the hairiest slide of all, but I will take you through just to very, very quickly and show you what the major contribution of this methodology is. The major contribution is that we can specify a well-defined objective function. We say, this is my error variance on my reconciled forecast, and I want to minimize that. And I minimize that with some pages of derivation, and it comes up with a P matrix that looks like this. So let me skip this slide and go to the next one and recap. We start off with a set of base forecasts for every time series that I have, 243. I use this P matrix that comes from my derivation. This P matrix maps those into the bottom level. Then I take this S and I bring them back up, and they're now coherent. Now, obviously, this P matrix is very different to the traditional P matrices. The traditional P matrix had zeros. We're zeroing out information. This one does not zero out information. This one combines information and might give a zero weight where it's needed. And it gives that zero weight through this W. This is a covariance matrix in here, which works as a weight. If you think about these weights, there's various ways of estimating this W. One of them is a WLS solution. So that's a diagonal matrix, and in the diagonal I have in-sample one-step ahead forecasts. Forecast errors. If that forecast error is large, because that enters with an inverse, that time series takes a small weight. If that forecast error is small, then that time series takes a large weight. So there's an inverse relationship between the forecast errors that I obtain in sample and the weight I give to that forecast that I combine. Okay, and that's it. No more technicalities. So if we can go back and recap. Remember, our approach says forecast everything we have, optimally reconcile them using this P matrix, and then bring them back up, and that will give you a set of coherent forecasts. If you're doing regression modeling, you'll identify this as a GLS estimator, and you identify this S times this as a projection matrix, where you're projecting onto the column space spanned by S, which is a coherent column space. If you don't do regression modeling, that's fine. Just remember that we have an approach that can take all the information you have, weigh it appropriately, and give you a set of coherent forecasts. Okay, so why did we do all this? What do we gain by doing all this? Here's our application. Let me remind you of the structure we have. We have the 4 attributes which interact to give you a whole set of 243 time series, which we need forecasts for. And we want these forecasts, as we said, to be coherent. How are we going to, well, we know that the forecasts, I showed you mathematically, the forecasts will be coherent because I'm summing them by the S matrix. The question is, how do we do in terms of forecasting performance? Have we completely wrecked our forecasting performance? Well, let me make a comment before I show you the results. In all the applications that we've done, it actually improves your forecasting performance quite immensely, and now we have theoretical results that show you why you're improving forecasting performance. So how are we going to evaluate what we get with the prisoner data? We're going to take our sample, which spans the period 2005 to 2016, and it comes from the ABS Corrective Service database. We're going to split it into a training and a test set. And then we're going to expand our window and do that multiple times. Now, for each training set, we're going to generate forecasts by 2 fully automated processes. They don't have to be these. They can be multivariate models. They can be whatever you like it to be. In my case, I'm just doing an evaluation, so I'm doing it quickly, and they work very well anyway. For each set of base forecasts, I'm going to again obtain a set of coherent forecasts by optimally reconciling by that P matrix that I showed you, or do a bottom-up approach, right? The traditional thing that I would do. And we're going to roll the window forward. I think that in the paper that's an expanding window, so that's a typo. And that will give us 12 one-step ahead per series. So 12 one-step ahead times 243 series. That's a lot of forecasts we're going to evaluate over. So all the noise gets washed out when we're aggregating over all these number of forecasts. Okay. So here's some results. What do we see here? On my horizontal axis here, on my vertical axis, sorry, I have mean absolute percentage error. So it's a percentage error, the larger, the worse the method does, okay? Across here, I have forecast horizon. So the first thing we notice is that all these lines increase as my forecast horizon increases, right? I'm less accurate 8 steps ahead than what I am 1 step ahead, okay? Now, let's look at each one of these lines. Let's start with the lighter colored ones, the light blue and the light red. These are the base forecasts that I get for the ARIMA and the exponential smoothing processes, right? So this is, if I forecasted all of these individually, independently, I didn't care about structure that I have, the aggregation structure, these are the MAPEs I would get. Now I take these and I reconcile them and I get these darker lines. And notice that the darker lines are below the lighter lines, right? So we improve in forecast accuracy. We get a smaller MAPE, okay? The other two lines here are sort of grey faded out. They're the bottom-up traditional way of doing it. And you see that the bottom-up actually loses in forecast accuracy, okay? This is for root mean squared error, just another error measure. And the thing to notice here is that if we consider root mean squared error, the bottom-up approach loses a lot. Yep, excellent. So, what we have here is, what I just gave you is on aggregate. So this one step ahead is across the 243 series, 12 times 1 steps ahead. Let's have a look at each level what happens, right? So this is the total. This is my aggregate level. This is, so my vertical axis has all the levels, states, sex, and the rest, and then two-way interactions, three-way interactions, and the very bottom level, okay? On my x-axis, I have a percentage improvement, so I decrease my MAPE as I go to the left if I get a negative value, and I increase my MAPE if I go to the right. So we see that for the levels, even for the levels, we don't expect to win all of them, because remember, this is a reconciliation process. I'm taking the best I can do for each individual, and I'm reconciling them so they can be aggregate consistent, they can be coherent. But you know, the results show that I'm winning almost everywhere, okay? Same thing for the ETS, so this is for the ETS model. Okay, in the last 3-4 minutes that I have, what I want to do is show you a little bit of the generality of this method by just introducing you to other settings that this has been used for. So far we've been thinking about a cross-sectional setting. We've been thinking about this point in time, I have attributes, I have geographical regions, I have whatever I have, and I want to forecast forward. The other setting that this has provided a lot of forecast improvement is when we consider the temporal setting. So if you think about this as a cross-sectional hierarchy, like the ones we've seen before, so total subdivides into x, y, and then into x, y, and so on. In the temporal dimension, I take the same thing, but what happens there, my bottom level is the actual time series itself. So I'm spanning the hierarchy across time. So this is my observed quarterly data, which I can aggregate up to semi-annual data, which I can aggregate up to annual. The idea there is that I forecast all these frequencies independently, and then I go and reconcile. Why do I do that? Well, think about the signal that each one of these frequencies give me, right? If I have seasonal data, once I aggregate up to the annual level, seasonality is washed out. I can see trend very, very clearly. It's not interfered by noise, it's not interfered by seasonal components. I can model trend up there much better than what I can down here. I can model seasonality probably better there than what here, because here I have some noise. But I don't want the noise to be forgotten, but it still stays there. So combining, bringing information from up to down or from down to up shows great forecast improvements. And you know, if you're interested, this is the paper that we do that in. So far I've spoken about cross-sectional, I've spoken about temporal. Obviously the next step is to join the two and do a cross-temporal, and that's when your S matrix starts becoming very, very ugly. So you have a structure, and within, you have a cross-sectional structure, and within each cross-sectional point you have a temporal hierarchy. And we've just completed a paper doing that and showing, again, forecast improvements all over. So what I want to leave you with is the two following statements, is that reconciliation, especially the cross-temporal one, the last one that we did, offers a single or at least an aligned view of the future to all decision makers, removing any organizational friction or misaligned decisions. More crucially, it offers a data-driven way to break within and between organization informational silos, right? We all work in crime, and I'm sure you don't know who the person next door who is interested in the indigenous aspect of the prison numbers does in terms of their forecasting, and what the other person looking for the female wards, or the other person in Victoria, or the other person in Queensland. But this way, the data tells us how to generate these forecasts, and the forecasts we get are coherent for everyone. They point for everyone in the same direction, in an aligned direction. Okay, here's a set of references. If you are interested in this, if you've got these data structures and you want to learn more, or if you've got a research assistant or a student or a colleague, the first point of reference would be this excellent textbook by my co-author and myself, dare I say. It's online and free, so I'm not trying to sell books, although you can buy it at a cheap price. And the more technical bits on these papers, which are one of them forthcoming and two of them forthcoming and they just come out, and the R packages that you can implement these, all you need to be is an R user, take the R package and implement it and generate more accurate forecasts for your data. Thank you. Four minutes to spare.
Well done, well done. Thank you very much, George. I know we're about to break for lunch, but we have time for some questions if we want. Yes, Don's very
Don, you're asking George or Don?
I'm asking you. I'm sure a lot of people will go to sleep tonight thinking about S matrices and H matrices, but here's a question which I'm sure is on the minds of many in corrections. Firstly, can that process be automated? Secondly, can you put a front end on it so that people who are working in corrections could pull out any particular forecast at any level they were interested in? Or do you have to be as clever as you to get answers to these questions?
So it has already been automated. The only thing you need to do is be an R user. You download the package, you read your data in, its instructions of how to do it. We haven't commercialized it outside R, so everything is free where you go and do it there. From your forecast, you don't even have to know the models that you fit. You can ask it to fit ARIMA models and it'll automatically fit with fairly sophisticated algorithms. You don't even have to do that. It will generate forecasts. You can pull out whatever forecasts you like. It's fully automated. As long as you're an R user, you can install R and go from there. And we are working, I should say that the last cross-temporal, or this contribution, which is exactly what people really want, where we are being coherent for short, medium, long-term forecasts, as well as the other direction. We're working on wrapping that into a package now as well. So all the stuff we do is open source. Everybody can get their hands on it. The data is available. You can replicate the results. That's how, at least, we work.
I have one question, but I think everyone's keen to get to lunch, so I'll just ask you for that. Can we please thank George for his presentation, and can we also thank all the speakers for your session? Yeah, so we might be a couple minutes early, but lunch is just going to be in the room out the back. Thanks, everyone, and enjoy the rest of the conference.